So today I'm going to talk a bit about visualization and visualization with using an external application. But the idea is that we will be able to export the results from your application in a format that you can open with this tool that I'm going to talk about today. So ParaView is an open source application. It's you can download it for Windows, Mac, Linux, and it's a Swiss Army knife of visualization. So you can visualize most things in this application. So I'm going to go through what it is and some usage and how you can access it from Python as well. So I will not do too many slides. These slides are from the foundation that is maintaining this. It's actually a software that is from Sandia National Laboratories in the US, and also the company distributing is called Kitware. So I will tell that. So it's open source, flexible, and you can also add things to this application as well. You can build your own extensions to it. So visualization as a concept is going from simulations to something that you can interpret. So usually when you do visualizations, you get you have a lot of arrays with results that it's hard to interpret numbers in a table. So using ParaView, you can go from numbers to something like this. So you have here flow simulation results. Most of them are flow, but there's also you can do chemistry applications, fire simulations, so on. And you can combine them in different ways, and you can do cuts and visualize streamlines and lots of things. Skip that one here. Just to get a hint of how much you can do with ParaView. So these are how many cells, in this case cells, these corresponds to finite elements in this application here. So I think this has increased a lot today. So you can run 6,250,000,000 cells and visualize them quite well in ParaView. You can also run it in parallel on supercomputers to visualize really large simulations as well. So ParaView is part of a kind of an architecture. And if you start from the lower parts here, it's built on top of OpenGL, which is a programming standard for hardware accelerated graphics. So that communicates with your graphics card, for example. So, and then it's also based on MPI for doing parallel work. It's not something we're going to do in this course. But the important stuff is on top here. This is something called VTK. And that is it's the visualization toolkit. And that is a C++ library, just like Qt, but contains both algorithm for visualization and code for actually rendering the graphics itself. On top of that, we have the ParaView server. So this is always started. And on top of that, we have the user interface. And ParaView itself is implemented in Qt, so the same toolkit that you're using in this course. And what you're going to download to this course is the ParaView client here, and that contains all these layers here. So it's basically a Windows application with toolbars, but that can take data and visualize the data. Skip that one here. So the idea of visualization, as I said before, is going from the left side here, numbers, to something that you can interpret. So what are the pressure lines or the density, pressure in a simulation? So basically, it's kind of a microscope for looking at visualization data or simulation data. ParaView can support different data types that you can visualize on. So you probably recognize a lot of these from finite element. So from the left side here, we have a uniform rectilinear mesh. So basically a mesh consisting of rows, columns, and stacks with the same distance between them in each dimension. You can have a non-uniform rectilinear grid. That means that you have a grid, but you can vary the distances between the cells. And that could be good if you want more. If you have a lot of happening in your simulation, you can increase the number of elements at certain points. You can do curved linear data. So that is basically a grid, but it's curved according to a certain rule. And then you can have the polygonal data, which is basically an unstructured mesh. It's what you get when you do your visualization in your code with the triangles that are, you fill the geometry with triangles. This is the same thing, but going in 3D. And then you have also an unstructured grid that is basically any element that you want to combine together. And so it's, yeah, I will show this example here as well. There's a lot of help here, I'll skip that. So I will go through basically how you use it, and I will start by skipping the PowerPoint slides and going directly to the user interface. So if we switch here, this is how the user interface looks like. And in this case here, you have different parts. So you have the normal user interfaces here. You can open things, close things. Here you have tools for manipulating the view. The resulting visualization comes up in this window here. And on the left side here, you have the more important thing here. So the pipeline browser area is where you put in your results. Your data. And you add data to this pipeline, and you modify the pipeline afterwards. So the first thing we're going to start with is we're going to create a sphere. So in your case, you will probably load data here, but just I want to show how the program works. So I'm going to just illustrate that with a basic shape here. And what you also notice here, there is a closed eye here. And that means that it's not visualized yet. And that is something that, by default, ParaView can handle a lot of data. And sometimes just the process of getting data out here takes a long time. And that's why you don't want to apply the visualization directly. You want to modify the parameters first. So you can see here also there's a green button here. And that means that we have data that can be visualized. So if I press apply here, I get a sphere here. And I can also continue down here. So you can see here, you can set the position of the sphere, the radius. So I put the 1 here, press apply, it grows larger. Every time I change something, the button turns green. You can also increase the resolution here. So let's do 16. And in the other direction as well. And you get a more smoother curve here. You can visualize these. You can change the appearance of the visualization here. By default, it says surface, but you can also go to points here. Then you see the points of the sphere. You can go to surface, what we have here. You can also go to wireframe. And here you can see the elements that the sphere is constructed of. And you can also have surface with edges, so you can see both the wireframe and the surface at the same time. And then I just go back to surface again. You can change the surface here as well. This sphere doesn't contain any data, it just is a geometry. So you can see here that I can switch to solid color is the only option except for normals, but that is the important thing. And you can change the color here, for example, going to red, like this. And then you can also change transparency like this, so you can see through the sphere. You can also make it more like plastic, like this. And you can also add data access grid here, so you can see where in space you are. And you can change here as well, different things here. So that is done here in the properties section here. So what you can also do here, so this is the first step in the pipeline. I can now apply filters to this pipeline. Let's see here. So I can do, so sources is where you get the data. You can have data that you read from disk, but you can also have, like we have here, geometry data here. And filters that manipulates the data coming in here. So I'm going to, shrink. You can see that there is a lot of things that you can apply. So this is the, if you go to alphabetical, you can see all the filters you can apply. So what I'm going to do shrink. So now you can see I added a filter and it adds to the pipeline. So the sphere is the first step, and next you apply a filter to that, and shrink, that shrinks the elements of the sphere. So you can see I have a shrink factor of 0.5, and you can see that I have ready data to visualize here. Now you can see here that it shrinks every element according to a factor here. So I can do really small, I can do a bit larger like this. And here you can see also that the previous step here is hidden, but you can always turn on this again, so you can mix them, and then I can change here the opacity of the outer sphere here a bit. I can also do see here. I can, for example, add a transform filter here. Let's see here, I can do this one here. Filters. And then here I can change the scale as well in different directions. Let's see, we'll do 1.5. Now you can see I scaled one of them a different size here. So you start with your initial data, and then you build filters on top of that. So, but this is not so really fun here, so we will go to work with real data instead. So what I'm going to do now is I'm going to do reset. So when you want to start over in ParaView, you press the reset session here. So you don't work in a document, you always work in a session, and you reset that session, and then you can save the session here by pressing File and Save State and Load State. To be able to export data to ParaView from your code, we are going to use a module called PyVTK. And PyVTK is not a graphical module. This is a module that exports the VTK format. And you construct this format by adding points, adding nodes, adding cells, and so on. And as I said before, these are the basic data types that ParaView supports. So grids of different kind, unstructured points, polygonal data, unstructured grids. So first I'm going to just do install VTK here, because PyVTK is not available in this notebook, so I'm going to run this here. So what we're going to do here now first is just going to look at how you create structures here. So you can import here using PyVTK import star. And then you create objects to define the data. So we are going to create polydata object. And then you specify the points, just as you do with Cordon EDOF. You define the coordinates, and then you have defined the polygons by defining the topology that refers to these points here. And then we add data points to this here. So here you can see that 1, 2, 3, 4, 5, 6, 7, 8 points. And you can attach data to be visualized in points, in the nodes, but also in the cells. So, and you build up the data, and these data that are going to be visualized on the structure itself. So you can see, I just add point data here. There are 8 numbers here from 0 to 7. And I name this data range sample scalars. Let's see, we'll run this one here. So this is the kind of the geometry. And this is the data I want to attach to the geometry. And then you can also add cell data, that is data that are part of the elements in the middle of those. So in this case, I have cell scalars. And we can see here I have 1, 2, 3, 4, 5, 6 polygons. And I add scalar 0 to 5 for each of these polygons. The normals are just to kind of visualize them. That is for the lighting calculations. And then I have some other data here as well. But the idea is when you have put all these things together, you create a VTK data object. And you combine the structure with the point data and the cell data objects that you created previously. And then you just save it. And you can save it in different ways. So the first way is you save it as an ASCII file, as a text file that you can open in Visual Studio Code. You can also save it as a binary file. And if I run it here, so now you can see in my folder here, I have these 2 VTK files. So the files have the extension VTK, and they look something like this. So this is the file format that the PyVTK module will generate. So you can actually generate this yourself if you want, but you can also let PyVTK help you with that. So what I can do now is I can go back to my ParaView. I have to download this one here. Then I open ParaView again. And now I do open downloads. Where did there? Example 1, VTK. Open. And now you see again, now it says, instead of sphere, it says example1.btk. So now we have loaded this file, and you can load it into our visualization by pressing apply. And you can see here that immediately we got something on the screen here. And it consists of 6 sides, so it's a cube. And you can rotate here like this. And if you look at the surface, you can see here that we have the surfaces here. Actually, we define them as polygons with 4 sides here. So, I don't know why I draw a triangle here, but that's probably visualization. But the idea here is that the numbers we pointed to, so you can see here that the color scale here goes from 0 to 7, and that is the numbers we put in the nodes here. So each node of this cube now has the number that we specified in the here, point data, scalars. So the nodes each have a scalar value. And you can also see here that in the display here now, properties, we have coloring sample scalars. You can also see that we have other data here as well. A point here means that the data is attached to the node. The cells means that the data is attached to the cells. In this case, the cells are the polygons, the sides of the square. So for example, we put cell scalars here instead. You can see here that it colors the entire surface with the numbers we added here. So we can see the color scale go from 0 to 5, which corresponds to the cell scalars here. You can move back again to sample scalars like this. So this is a very simple example. In this example, the next example here, we have structured points. So it's a structured grid where with 3 by 4 by 6 sides, and then we provide the scalars directly here. So here we do everything in a single statement here. We create the So in this example here, I have I define the structured grid here by it's 3 by 4 by 6, and then I define all the values for each of the points in that structure. So if we go to ParaView again, so now we have a model here, and we want to do another model. We do the reset button here, and we do yes. Then we do open, and then we go to example 2, where did it go? There. Okay. So now you can see here, it shows you this is outline here. So let's go and look at surface with edges here. So now you can see here, we have 3 by 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So now we get a structure grid like this. And now we can go in here and look at, so if you don't specify a name, you get, PyVTK will name the arrays that you want to visualize by numbers. So scalar 0 is the first we have here. And now you can see here that I have values here inside here that is that corresponds to what we have in this field here. So these are the values here. So for example, if I change here 1 to 150 and run this again, now I have to reload this again. I think I can do that. Okay, how do we reset again? Now you can see here that I added a point here with 150 here, and you can see that it visualized it like this. So go back here and go back. Reset. What we can do now is we can actually, okay, I didn't change that. we can cut this in two, so we can look inside here and how the data is configured. We can do this here by using the clip filter. And when you add a clip filter, you can see here that you get a cutting plane, and you can change this plane here in properties here. You can change the normal. So in this case, the normal is in the X direction, but you can also do Y and Z normal. So let's cut in this plane here. And this here checks if you want to have the plane visible when you're working. That could be a good idea when you're experimenting with where you want to cut. Then you do apply, and you can see here that you can look inside. What you can do is as well, you can actually move this plane, and you can see what's inside here. So it's a way of kind of looking inside your model and for things that you don't see normally. So if I remove this one here again, what you can do as well, which is really cool, is that you can actually enable the original block here, and you can make this transparent. So now you can see that you can have the outline of the existing, the complete data block here, but you have a cutting plane inside here. So if we can modify this again, I can change show plane, and I can move it back again here, apply. So you can see the outline of the complete structure here as well. See if I go back to my... What you also can do is that if you have an existing structure, you can do you can use that structure that you already have. So here you have VTK data, and I want to use only the structure. And then you can see here that I append. You can create a function here that we want to calculate for each of the nodes. And if I put only structure here, it will use the structure from the example 2 VTK. That's the one we saved here. And we use that for the structure, and then we provide this one for the function that we'll visualize here. So we call this the file example2fsp. And I just do like this. You ask for a commenting function. You can do like this: edit toggle line comment. Then it puts comments in front of everything. So let's run this again, and now you should have an example2f. So it's just now it uses a structure from the previous example here. So you can see here that you have the same geometry, and then you can see here that we created a function here field that we want to visualize here. So now you can see I get a more smoother visualization here of the function that we had provided. I'll skip those two here. In the final example here, there's also a possibility to kind of generate any kind of geometry for ParaView. So in this case, I have a set of points. I also have vectors here. So up until now, I've only visualized scalar data in either the cells or in the nodes. But you can also visualize vectors and put those in the nodes or in the cells. So here I create a VTK data structure with an unstructured grid. That means that you can put you can have points, you can have hexahedrons, you can have tetra, polygons, triangles. You can mix and match. And then you add the vectors here and a scalar range here as well. So let's run this. Hopefully it will work. Yes. And then we go back to ParaView, and this should be the example 3. Reset to start over. And then we go example 3. now we get this strange objects here. So it actually consists of, if you look at the wireframe here, both triangles, polygons, no, there is also lines here. This is a line here. And now it's colored by the scalar values. So they go from 0 to, I think it was 0 to 26. So that's this color scale here as well. Let's see, checks out. So let's switch to surface. You can also visualize the vectors here. And vectors can be visualized using this filter here called a glyph filter. And a glyph filter will place symbols oriented in the vector's direction. So if I do like this, you can see I get a glyph here. And then you check what kind of glyph do you want. So in this case, the default is arrow. And that should be pointed in the direction of the vector. So we put orientation array, that is the vector 0. The scale array, we scale by the size of the vectors here. And scale by magnitude. And here you have a scale factor as well. So just, and if you have a green button here with 2 arrows pointing, that is, it calculates the scaling factor according to the data available. So now it puts 0.6 here. So now you can see here that I get arrows here, and those represents the vectors in the vector field. And you can also visualize using lines here, for example. So if you have a lot of vectors, these vectors can be heavy on the computational side. So here you can see I visualize the vectors using lines. You can also do coloring here. So for example, if you're only interested in the direction and size of the vectors, you don't want to have a color. You can just put solid color here, and then you displace the vectors in white. Let's see, I can do arrows here. And now you can see all the arrows are gray like this. So I will also show you how you can use this in your examples here, what you will generate here. So hopefully I will have an example of that as well. So there are functions in CalFrame to generate these VTK files. And I will see if I can find them here. Let's see here, I can take this parameter. So you probably recognize this one here. So this is it visualizes the von Mises stresses here of your problem, stress problem. So that is a single cell value that you put inside that you visualize for each of the cells here. And what you can do here as well, you can see I have a color scale here, and that shows von Mises. You can change this color scale by going down. You have here this folder with a heart. And you press here, you can select different color scales for the stresses. So let's do, let's go take. We take a bi-radius map here. Apply. And now you can see I changed the color scale. If I want to visualize the principal stresses, those are vector fields here. So you can see here I have principal stresses as vectors inside each cell. To visualize those, I have to add a glyph field here. So I add the glyph here, and we can start with a line here. And then we check the field I want to visualize is principal 1. Scale array, principal 1. Apply. And we press apply here. Okay, they are a bit too big. Let's see here. Okay. Here you can actually scale them a bit. And if we zoom in here, you can see This is the main principal stresses here going in, and we can change the color here to solid color here instead, so you can see them better. So these are the principal stresses. And if you want the second principal stress, we just add another glyph here. So we select param stress again, add a glyph, and then we put a line here. We select principal number 2, auto calculate, and then we set the color to. Where does the color go? Okay, we perhaps do apply it directly. Solid color here. The thing is that if you do it like this, you get the scaling is wrong here. So the second principal stress should be smaller than the main principal stress. So if we go back here again to glyph 1, we have a scaling factor here. So if I copy this one here and go to glyph 2, put the same scaling factor here, then you get the correct scaling factor of this. So, but there's no way of visualizing principal stresses in ParaView, but the way you do it is you do visualize 2 vector fields. So this is this for the stress problem. Same thing for the flow problem, that is a temperature problem, or the groundwater flow. So we go in here, open up. I think I have a... Oh, that was the wrong one. Okay, I don't have the... but for the stress problem, or the flow problem, you have the same thing, but then you have the max flow as a single point in the node, that is the element values. Then you also have the pressure height or the temperature in the nodes. So I'm just going to go back to a previous example here. I guess I forgot how you visualize the... So you have one field more. You have also the displacements here. And if you want to visualize the displacement on your mesh, you need to select this, select this one here, and do warp. And then warp by vector here, and you select the vector field, that is the displacements, and you do a scaling factor here, and then you apply. Then you can see here that it warps the mesh according to the vector field. And here you can combine that with the original mesh here. So if you turn that on, we make that transparent. And we put a wireframe here. So here you can see how the deformed mesh is. So you have a lot of options in ParaView to visualize your data in different ways. You can do similar things with the flow problem. I just didn't find my data for that. So that was a bit about ParaView. So ParaView is something that you can, it's not only for structural mechanics, anything that have data in a grid-like or unstructured grid-like, where you attach data to node points, cells, you can visualize in ParaView. As I said before, there is a lot of filters here to do data processing. So let's take a break here. And after the break, I will talk a little bit about the things you have learned now with Python, how you can use that on larger resources like supercomputers. I will show you high performance computing, what it is, and how you can take advantage of using Python on supercomputers as well. So, but that will be in 15 minutes.